Here's a time scale that's often used in geology for sedimentary layers. It's not very clear in this picture. Worldwide changes in index fossils determine where your breaks are in this case. That's in the Cambrian and all up. In the Precambrian, then they have to use other things besides index fossils. Fossils, however, do not give us numerical ages. Where do these numbers come from over here then? How do they arrive at these numbers? Now let me explain a little bit about what index fossils are. In certain layers you find certain fossils that are very prominent in those layers, and those are what we call index fossils. They've associated them with ages, but how do you arrive at these ages? The methodology of dating sedimentary rocks is you use index fossils or help to correlate that. Sedimentary rocks with similar index fossils are grouped into geological units or layers. These geological time units then are based on the evolutionary assumptions of fossils. This methodology, as I explained, of dating sedimentary rocks is circular reasoning with fossils, the ages determined by evolutionary theory, to date the sedimentary rock, and in turn, then the sedimentary geological layers of sedimentary rock are then used to date the fossils. You can't get out of the loop. But there's no objective way to determine how old those fossils are or the geological layers just using this system. Let me give you some examples. Clams, where do they come from? As you look, these are a bunch of different clams. Linguini, clams. And you'd say, well, where did they come? When did they develop into things? But we go back and we see these different clams, and they're mollusks, and that they come from this period of time here. They span that whole period of time. So you say, that's how old they are. You see what I'm saying? You don't have an objective way to date the things. You come back to, how old are dinosaurs? You look at dinosaurs and you say, well, they're found in this Mesozoic age. And they look back and they say, well, the Mesozoic ran between the 65 million years ago and 290 million years ago. So that's where the dinosaurs are, and that's how old they are, because they fall in this Mesozoic geological layers. Let's go to a more objective way that they've tried to use of dating getting these old ages. This is using radiometric methods. There's radioactivity of certain elements are used to attribute old ages to the Earth. How's radioactivity used to measure the age of the Earth? Certain parent elements decay into other daughter elements over a long period of time. Let's look at the atom, for instance. You have the atom or an element, and the whole universe is just made out of atoms and elements. What they are is they're the fundamental unit of matter. And you have protons and neutrons in the nucleus, and you have electrons on the outside. Radioactive decay has to do with the degeneration of the nucleus, and then it affects the electrons on the outside. But radioactivity has to do with the decay of the nucleus. The phenomena is that certain elements such as uranium and thorium are unstable. They're bigger. In this case, they're big atoms, and their nucleus is a little hard to hold together. And occasionally, what comes out of this is that this is the parent, say uranium, and then it'll decay down to thorium by a loss of 2 protons and 2 neutrons. And the uranium in that case is the parent, and the thorium then is the daughter. Thorium then will in turn degenerate by an alpha decay down to radon. And it goes on down until it gets down, and we'll see a chart of it here later. It goes on down to lead eventually before it becomes stable. Radioactive decay, as we said, is a parent going to a daughter. In the case of uranium, through a series of decays, it goes down to lead. In the case of potassium, it'll go to argon, which is a gas. This is an alpha particle decay, and again, what an alpha particle is just the nucleus of a helium atom, and it's 2 protons and 2 neutrons, and they come out of the thing. They're knocked out, and they'll emit this, 2 protons and 2 neutrons, and that's called alpha decay. In that case, the parent atom drops down to 2 numbers, drops down to 2 numbers, like you jump from uranium, and it'll drop back to thorium. It drops down 2 numbers, atomic numbers, in alpha decay. Beta decay is a little bit different. It actually moves up the scale, like rubidium to strontium. In this case, a neutron is made out of an electron and proton. And the neutron will lose the electron, that's a beta particle, and it'll leave a proton, and actually you move up the scale. You go from rubidium to strontium, which is actually higher on the atomic scale. So we've talked about alpha decay, beta decay, and there's one other kind of decay that's common, and that's where actually a proton in the nucleus captures one of its electrons or a loose electron and forms a neutron in the nucleus, and again it becomes it moves down the scale because it's gone from a proton, it's lost 1 proton and gained a neutron in the nucleus. Okay, now this is uranium to lead decay. And you see how you start out with uranium, it goes to thorium, uranium, then it drops down through a series to polonium. Polonium then goes to lead, and then that jumps back to polonium and then on down to stable lead form. And this is a radioactive decay. And eventually the parent, uranium, ends up as decays to its daughter lead in a series of decays. The rate at which this process occurs is measured in terms of half-life. Let me give you an example. You know, an hourglass tells you so much time. And what it is, a half-life, is you start off with the thing full. A half an hour later, you've lost half of your sand has gone to the bottom. That's a half-life. However, in the decay then is you don't let the rest of it run through. You take this half and run it through another hourglass. So your half of it is cut in half again, so you end up with 1/4 after a full hour. Let me show you in a chart. The rate of decay is measured on how long it takes for 1/2 of the parent element to decay to a half-life into a daughter element. Example, let me give you, of carbon-14. It has a half-life of 5,700 years, okay? That means that after 5,700 years, if you started with 10 pounds of carbon-14, you'll only have 5, okay? In the second half-life, however, you only have 5 to start with. So in 5,700 years, again, you only have 2.5 pounds. And then you start with 2.5 pounds and cut that in half again. So in each half-life, you lose half of what's left. So that's what's called a half-life. Now here you can see the decay. If I start off with 1 pound, here's the first half-life, I only end up with 1/2 pound. In the second half-life, I only end up with 1/4. Third half-life, I only end up with what? 1/8. So this is what we call an exponential decay. And that's the way you measure radioactive decay. These are commonly used for dating systems: uranium to lead, thorium to protoactinium, potassium to argon, argon's a gas again, rubidium to strontium, carbon-14 to carbon-12, and then you have various elements that go to helium. Now we're using, in these cases, radioactive decay is what they call fission. That's where the atoms break down with time. In fusion, you don't use that for dating. That's where you take, say, 2 hydrogens, like is taking place on the sun, and put them together, and they're fused together to form a helium. That's what we think is heating the sun, is fusion. In an atomic bomb, you have fission, they're breaking. In a hydrogen bomb, you're putting them together, but you can't use fusion reactions to date with. They're unstable and very difficult to measure. Here are some half-life times that we take. These are the parents, the radioactive parents. Uranium-238 goes to lead-206. It takes 4.5 billion years for half of it to decay to that. Uranium-235 to lead-207 takes 713 million years. Thorium to lead, rubidium to strontium, that's like 47 billion years. Potassium to argon, 1.3 billion years. Now, these are built on the assumption that these decay rates are constant. However, that is not true. Let me give you an example. Let's take uranium-235 going to lead-207. It says 713 million years. I can go down here at Wolf Creek power generating plant, and I only enrich my uranium-235 to 10%. I put it in that reactor, and you know what the half-life goes to? 2 years. I take it from 700 million to 2 years. I can take the same element, enrich it even more, uranium-235, and I can put it in an atomic bomb, and I'll reduce its half-life to nanoseconds, millionths of a second. It depends upon the outside radiation. Those are all self-energized. I can put radiation in from another source and do the same thing. If uranium-235 was created in high concentrations, its half-life would be in a matter of seconds or minutes. And in fact, we have found, the French in Gambo have found natural atomic reactors. They had meltdown. The half-life was not 713 million years. It's a very short amount of time. So these things can change. The assumption, however, in using these systems is that these are all constant. They're never constant, and they can be changed with external radiation. So, what can we use these for? These radiometric dating. They can be used for igneous rock, that is rock from volcanoes, or we can use them for metamorphic rock. That's like basalts. However, we cannot use them for sedimentary rocks such as limestone, sandstone, and shale. Why is that true? Why can't the radiometric methods be used for sedimentary rocks and fossils which are found in them? Sedimentary rocks, one, are composed of another material that was brought in from someplace else. It's not original material. So what are you dating? Are you dating the stuff that came from another place? Yeah. But it's been all changed in the process. One of the, as you're going to see, one of the assumptions for radioactive method is it can never be changed. It can't be contaminated and it can't be moved around. So you can't date sedimentary layers. Secondly, it's not possible that it can be used for dating fossils because the original plant or animal material that made up the fossil has been replaced with non-organic material, minerals. So the calcium in a bone, a fossil bone, is not the calcium that was in the bone when it was alive. That was organic calcium. That no longer exists. It's inorganic calcium. So what are you dating? The calcium that came from someplace else. You cannot use these for sedimentary methods. You'll see people who date, well, this fossil's 500 million years old. And you say, wait a minute. How did you date that? With what? What are you dating? So they'll try and use it of igneous and metamorphic, but we'll see that also has some serious problems by using scientific methods. Now, these are the radiometric dating assumptions. The starting amount of the daughter is known. In most cases, you assume that there's no daughter. It's all parent. It's all uranium, no lead. Okay? Or if you knew it, you knew how much it was. And they'd use a system called an isochrome to try and determine what was the original amount of daughter to begin with a thing. I could take some uranium, lead, fire it together, bring it to you, and you'll date it at 700 million years old because it's been through a half-life. I just made it yesterday. To be right with this system, you have to know how much you start with of the daughter, how much lead you started with. Also, you assume that all of the daughter element is due to radioactive decay. Okay? You couldn't do that in the case where I fired it and brought it to you, because I had already started with lead. Thirdly, the sample must be in a closed environment. You cannot have contamination coming in and changing anything. And that's virtually impossible in the world where everything's in this rock cycles and everything else. There's nothing practically on the face of the earth that's been uncontaminated in its half-life. Lastly, we assume that the decay rate is always constant, and as I pointed out, that can change depending upon the radioactivity or radiation that it receives from the outside. If we got a burst of cosmic rays, for instance, it'll change dramatically these decay rates. Let me give you some examples of radiometric dating problems. Sunset crater in North Arizona. We know that that took place in 1065 AD, okay? But what does it date at? 200,000 years. This is using potassium argon. And why they use potassium argon is argon's a gas, and so it should start off with 0 daughter, because this is in a crater deal. There shouldn't be any argon to start with, and yet there's enough argon that it dates at 200,000 years old. We take lava flows in New Zealand. Again, potassium argon, because you assume that all of the gas is gassed out in the lava flow. We know that it took place in these samples in 1949, 1954, and 1975, and yet it dates at 275,000 years old. Hawaii, another volcanic flow, basalt, potassium argon, assuming that the argon's boiled out. It took place in 1801 AD, and it dates from 4.4 to 22 million years old. Mount Etna in Sicily, we knew it would take place in 1972. It dates at 140,000 to 350,000 years. Our one here in the United States, Mount St. Helens, we know it went off in 1980. You go out and date the ash from that, again using potassium argon or argon to argon isotopes. And the youngest one you have is 200,000 years. And yet it took place only 30 years ago. And some of them are up to 2.4 million years old. Here you have a case of the Grand Canyon. You have volcanic layers up on top. Again, in this case using rubidium to strontium isochrones, which should eliminate what the initial state was. They date them at 1,340 million years, 1.3 billion years, okay? We know these flowed in historical times, the last several hundred years. You go down on the bottom with the basalts, and this is in Precambrian, no sedimentary layers, volcanic flow, and it's only at 1.07 billion years. And it's on the bottom of the Grand Canyon, and this older one's on the top. And we know that this one only flowed a few years ago. It's in the last several hundred years. Because there were Indians that saw it flow. So what you have here is, how can you trust the thing? And yet they date all of these things in between the sedimentary layers. You can't date them, so you use what? Your igneous, your volcanic. And what happens is you end up with one that's 250 million years older at the top of the canyon than you do at the bottom.